All right, so we're going to do another Physics 2 example. This one also is related to Coulomb's law. There's a little more to it, but that's okay. This is more of a problem you might see on an exam for an example. So this is the question, and this is the figure. It says two mass, m equals 6g point charges on a 1 meter long thread repel each other after being charged to Q equals 110 nanocoulombs, as shown in the figure. They want us, I didn't have this part saved, but they want us to find theta. So this was sent to me first off by a student that had a question, and if you want to ask me a question, you can follow me on Instagram, _physics_tutor. Send me a picture of the problem and anything you're specifically struggling with, and I can try to help you out. And someone sent me this. This is related to one of the playlists I'm doing, so I figured this is perfect. So to start, we actually start off with a situation kind of like this, where they're together and because there's no charge, there's no repulsion force. Then you give them charge, and you end up with the situation they give us here. These are still length L. And then they both have a positive charge of 110 nanocoulombs. So what that means is they're going to repel each other equally. So this angle is the same as this angle. Okay? They're both positive charges, so they repel. So we'll make sure we understand that. And now we're at our problem. So the question is, what is theta? Well, a good place to start is to always draw pictures. And we started that. We drew a couple pictures. But namely, I want to draw some free body diagrams. There are always good things to do when you know there's forces acting on your objects. And turn that down. Must be a good channel. I'm subscribed to them. So let's do that. We can do it. I'm going to call this mass 1 and this mass 2. Yes, they're the same, but it's fine. You can look at either one. I'll just look at mass 1. So I'll draw the red dot. Now, what forces are acting on it? I like to start with non-contact forces. So gravity, which is just mg. Sometimes with these problems, there's not always a weight force, but because these are 6 grams, it mentions in the problem the masses are 6 grams, there's going to be a weight force. It's not something that can be neglected. Are there any other non-contact forces? Well, yeah, right? We have the force from 2. They're repelling each other. The force, I'll just say force of 2 onto 1. That's what moved it from here to here. And then we have a tension force, which has components. So this is tension. This is that angle theta. Tension in the y direction is t cosine of theta by just doing some right triangle trig. And tension in the x direction is t sine of theta. Okay? You could draw the free body diagram for the second one as well, but it's not necessary. I'm just going to draw it with 1 because they're essentially the same thing. Okay, so we have that. I'm going to write down what we know, because that's always a good thing to do when you don't know what to do. Just write down what you know. So we'll do that here. No/unknown. Guess I should say known/unknown. Well, we know the mass is 6 grams, which is 0.006 kilograms. 1, 2, 3. We know the length L is 1 meter. And we know the charge Q is 110 nanocoulombs, or if we convert this, 110 times 10 to the negative 9th coulombs, which it's always good to just convert to coulombs. And then I'll go ahead and make note that theta is kind of the big picture idea. That's what we really want to know. So I'm going to box that just so I have it for reference. So we drew the picture, we drew a free body diagram. Whenever you draw a free body diagram, it's almost pointless if you don't do Newton's second law. So we'll start by saying the sum of forces in the x direction is equal to mass times acceleration in the x direction. Now, as shown here in the picture, it's not moving, it's not accelerating. It's reaching kind of this equilibrium. So there's no acceleration in the x direction. So the sum of all forces in the x direction, well, let's look at our free body diagram. We have, and just for the record, let's draw it in green. We'll let this be positive y, this be positive x. There's no need for a z direction. So our positive in the x direction, we have this part, and that's t sine theta. So we have tension times sine of theta, and then we have this force, which is in the negative direction. It's to the left of our origin. So minus the force of 2 onto 1 equals 0. Or t sine of theta is equal to force 2 onto 1. Now force 2 onto 1, that's coming from the push of 2 onto 1, the repulsion force, which is given by Coulomb's law. And we've talked about Coulomb's law. We know Coulomb's law. So I can replace that, t sine of theta, with k, the absolute value of q1, times q2, divided by the distance between them squared. Well, they both have the same charge, and they're both positive, so the absolute value is not necessary. So a number times that same number is just that number squared. And like I said, the absolute value is not necessary. Now, what about r squared? What about r squared? Well, let's look at our picture again. R squared, or r, is going to be this distance. This whole length from the first charge to the second is length r. The way I would recommend finding this is to think of this as its own triangle. So we created a right triangle. We know the length here is L. We know the angle here, well, we don't know it, but we're looking for it, is theta. Let's think about what this side is. Well, from 1 to 2, it's r, and they're both equally contributing to the push away, the repulsion force. So hopefully you can see that's 1/2 r. So we could say sine of theta is equal to 1/2 r divided by the hypotenuse of this red triangle, which is length L, Or if we multiply both sides by L, L sine of theta is equal to 1/2 R. If we multiply both sides by 2, then 2L sine of theta is equal to R. And that's the distance between the 2 points. So let's substitute that in. T sine of theta equals, we said it was 2L sine theta. 2L sine of theta. It's all squared. And we still have the K and the Q squared on top. Let's go ahead and square everything in the denominator. So we have K, Q squared over 2 squared is 4. L squared is just L squared. And sine squared is just sine squared. Now I'm going to multiply both sides by sine squared of theta, including this side. I don't have room. And I'm going to divide both sides by t. Sine squared theta. So the t's drop here, and I'm left with sine cubed theta equals the sine squareds drop here, and I have 4L squared times tension equals K Q squared. Now, one problem is, what is tension? We don't know tension. So we have to go back up here, and we're going to I'm going to try to give myself a little bit of room here. We're going to do the sum of all forces in the y direction is equal to mass times acceleration in the y direction. This is still 0 for the same reasons that this was 0. The forces we have acting in the y direction, well, we have a positive t cosine theta because that's above our origin, minus mass times gravity equals 0. Or t cosine of theta equals mg. Tension is equal to mg divided by cosine theta. So now we know tension. So let's continue. Let's substitute that in. Sine cubed of theta equals k q squared divided by 4L squared, and tension is mg divided by cosine of theta. Or if we were to cube root both sides, we get sine of theta equals k q squared all divided by 4L squared times mg over cosine theta. Now we have to use the fact that if you scroll up to the top of the question, well, it doesn't say it here, but it said it when it asked for theta to assume small theta. Now what that means is we can use the Taylor series for sine of theta, which is about theta, and cosine of theta for very small angles is about 1. You could also think of this as the linearization. Okay, so if that's the case, I can replace sine of theta with just theta and cosine with just 1. So theta, which is what we were looking for, is the cubed root of k q squared over 4L squared, mg divided by cosine of theta, but cosine of theta is about 1, so that's just mg. K is known, Q is known, L is known, mass and gravity is known. And let's see, when you plug this in, I just wrote this down somewhere. You'll get the answer in radians, so just right here. To convert from radians to degrees, which is what we usually use in physics, hopefully you remember 180 degrees divided by pi. And if you plug that in, you should get theta, I did my curly line wrong, is about 4.43 degrees. And that is the angle made. So hopefully that makes sense. I really like this problem. It used a lot of Newton's second law, so good refresher there. It used a little bit of geometry. Obviously, Coulomb's law was needed. Used small angle approximations, which is always good, and a little bit of algebra. So really the whole